Hi. Welcome to the second module of the Python Fundamentals course, which is about strings, collections, and iteration with for loops. Python includes a rich selection of collection types, which are often completely sufficient for even quite intricate programs without resorting to defining our own data structures. We'll give enough of an overview of some fundamental collection types now, enough to allow us to write some interesting code. We'll also be revisiting each of these collection types, together with a few additional ones, later in the course. Let's start with these types: str, bytes, list, and dict. Along the way, we'll also cover Python's for loops. Strings in Python have the data type str, spelled str, and we've been using them extensively already. Strings are sequences of Unicode code points, and for the most part, you can think of code points as being like characters, although they aren't strictly equivalent. The sequence of characters in a Python string is immutable, meaning that once you've constructed a string, you can't modify its contents. Literal strings in Python are delimited by quotes. You can use single quotes or double quotes. You must, however, be consistent. For example, you can't do this. Supporting both quoting styles allows you to easily incorporate the other quote characters into the literal string without resorting to ugly escape character gymnastics. Notice that the REPL exploits the same quoting flexibility when echoing the strings back to us. At first sight, support for both quoting styles seems to violate an important principle of Pythonic style from the Zen of Python. There should be one, and preferably only one, obvious way to do it. In this case, however, another aphorism from the same source, practicality beats purity, takes precedence. The utility of supporting two quoting styles is valued more highly than the alternative, a single quoting style combined with more frequent use of ugly escape sequences, which we'll encounter shortly. Adjacent literal strings are concatenated by the Python compiler into a single string, which, although at first it seems rather pointless, can be useful for nicely formatting code, as we'll see later. If you want a literal string containing new lines, you have two options: use multi-line strings or use escape sequences. First, multi-line strings. Multi-line strings are delimited by 3 quote characters rather than 1. Here's an example using 3 double quotes. Notice how, when the string is echoed back to us, the new lines are represented by the /n escape sequence. We can also use 3 single quotes. As an alternative to using multi-line quoting, we can just embed the control characters ourselves. Or, to get a better sense of what we're representing, we can use print to see the string. If you're working on Windows, you might be thinking that new lines should be represented by the carriage return new line couplet /r/n. There's no need to do that with Python, since Python 3 has a feature called Universal New Line Support, which translates from the simple /n to the native new line sequence for your platform on input and output. You can read more about Universal New Line Support in PEP 278. We can use the escape sequences for other purposes too, such as incorporating tabs with /t, or allowing us to use quote characters within strings by using a slash followed by the quote sign that you want. See how Python is smarter than we are using the most convenient quote delimiters. Although Python will also resort to escape sequences when we use both types of quotes in a string. Because the backslash has special meaning, to place a backslash in a string, we escape the backslash with itself. To reassure ourselves that there really is only one backslash in that string, we can print it. You can read more about escape sequences in the Python documentation at python.org. Sometimes, particularly when dealing with strings such as Windows file system paths or regular expression patterns which use backslashes extensively, the requirement to double up on backslashes can be ugly and error-prone. Python comes to the rescue with its raw strings. Raw strings don't support any escape sequences and are very much what you see is what you get. To create a raw string, prefix the opening quote with a lowercase r. We can use the string constructor to create string representations of other types, such as integers or floats. Strings in Python are what are called sequence types, which means they support certain common operations for querying sequences. For example, we can access individual characters using square brackets with an integer zero-based index. Note that in contrast to many other programming languages, there is no separate character type distinct from the string type. The indexing operation we just used returns a full-blown string that contains a single character element, something we can test using Python's built-in type function. There will be more on types and classes later in the course. String objects also support a wide variety of operations implemented as methods. We can list those methods by using help on the string type. Ignore all the hieroglyphics with underscores for now, and page down until you see the documentation for the capitalize method. Press Q to quit the help browser, and we'll try to use that method. First, let's make a string that deserves capitalization, the proper noun of a capital city no less. To call methods on objects in Python, we use the dot after the object name and before the method name. Methods are functions, so we must use the parentheses to indicate that the method should be called. Remember that strings are immutable, so the capitalize method didn't modify C in place, it returned a new string. We can verify this by displaying C, which remains unchanged. You might like to spend a little time familiarizing yourself with the various useful methods provided by the string. Finally, because strings are fully Unicode capable, you can use them with international characters easily, even in literals, because the default source code encoding for Python 3 is UTF-8. For example, if you have access to Norwegian characters, you can simply enter this. Alternatively, you can use the hexadecimal representations of Unicode code points as an escape sequence prefixed by /u, which I'm sure you'll agree is somewhat more unwieldy. Similarly, you can use the /x escape sequence followed by a 2-character hexadecimal string, or an escaped octal string to include Unicode characters in a string literal. There are no such Unicode capabilities in the otherwise similar bytes type, which we'll look at next. Bytes are very similar to strings, except that rather than being sequences of Unicode code points, they are sequences of, well, bytes. As such, they are used for raw binary data and fixed-width single-byte character encodings such as ASCII. As with strings, they have a simple, literal form using quotes, the first of which is prefixed by a lowercase b. There is also a bytes constructor, but it's an advanced feature and we won't cover it in this fundamentals course. At this point, it's sufficient for us to recognize bytes literals and understand that they support most of the same operations as strings, such as indexing and splitting. You'll see that the split method returns a list of bytes objects. To convert between bytes and strings, we must know the encoding of the byte sequence used to represent the string's Unicode code points as bytes. Python supports a wide variety of encodings, a full list of which can be found at python.org. Let's start with an interesting Unicode string which contains all the characters of the 29-letter Norwegian alphabet, a pangram. We'll now encode that using UTF-8 into a bytes object. See how the Norwegian characters have each been rendered as pairs of bytes. We can reverse the process using the decode method of the bytes object. Again, we must supply the correct encoding. We can check that the result is equal to what we started with, and display it for good measure. This may seem like an unnecessary detail so early in the course, especially if you operate in an Anglophone environment, but it's crucial to understand since files and network resources such as HTTP responses are transmitted as byte streams, whereas we prefer to work with the convenience of Unicode strings. Python lists, such as those returned by the string split method, are sequences of objects. Unlike strings, lists are mutable, insofar as the elements within them can be replaced or removed, and new elements can be inserted or appended. Lists are the workhorse of Python data structures. Literal lists are delimited by square brackets, and the items within the list separated by commas. Here is a list of 3 numbers, and a list of 3 strings. We can retrieve elements by using square brackets with a zero-based index, and we can replace elements by assigning to a specific element. See how lists can be heterogeneous with respect to the types of the objects. We now have a list containing a string, an integer, and another string. It's often useful to create an empty list, which we can do using empty square brackets. We can modify the list in other ways. Let's add some floats to the end of the list using the append method. There are many other useful methods for manipulating lists, which we'll cover in a later module. There is also a list constructor, which can be used to create lists from other collections, such as strings. Finally, although the significant whitespace rules in Python can at first seem very rigid, there is a lot of flexibility. For example, if at the end of the line, brackets, braces, or parentheses are unclosed, you can continue on the next line. This can be very useful for long literal collections, or simply to improve readability. See also how we're allowed to use an additional comma after the last element, an important maintainability feature. Dictionaries are completely fundamental to the way the Python language works and are very widely used. A dictionary maps keys to values and in some languages is known as an associative array. Let's look at how to create and use them in Python. Literal dictionaries are created using curly braces containing key-value pairs. Each pair is separated by a comma, and each key is separated from the corresponding value by a colon. Here we use a dictionary to create a simple telephone directory. We can retrieve items by key using the square brackets operator, and update the values associated with the key by assigning through the square brackets. If we assign to a key that has not yet been added, a new entry is created. Be aware that the entries in the dictionary can't be relied upon to be stored in any particular order. Similarly to lists, empty dictionaries can be created using empty curly braces. We'll revisit dictionaries in much more detail in Module 5. Now that we have the tools to make some interesting data structures, we'll look at Python's second type of loop construct, the for loop. For loops in Python correspond to what are called for-each loops in many other programming languages. They request items one by one from a collection, or more strictly, from an iterable series, but more of that later, and assign them in turn to a variable we specify. Let's create a collection and use a for loop to iterate over it. If you iterate over dictionaries, you get the keys, which you can then use within the for loop body to retrieve values. Here we define a dictionary mapping string color names to hexadecimal integer color codes. Note that we use the ability of the built-in print function to accept multiple arguments. We pass the key and the value for each color separately. See also how the color codes returned to us are in decimal. Now, before we put some of what we've learned together into a useful program, practice exiting the Python REPL with Ctrl-Z on Windows or Ctrl-D on Mac or Linux. In this last section, before we summarize, we're going to write a longer snippet at the REPL and briefly introduce the with statement. We're going to fetch some text data for some classic literature from the web using a Python standard library function called the URL open. To get access to URL open, we need to import the function from the request module within the standard library urllib package. Next, we're going to call URL open with the URL to our story. We'll be using a Python construct called a with block to manage the resource returned by the URL, since under the hood, fetching the resource from the web requires operating system sockets and such like. We'll be talking more about with statements in a later module, but for now it's enough to know that using a with statement with objects which use external resources such as this is very good practice to avoid resource leaks. The with statement calls the URL open function and binds the response to a variable named story. Notice that the with statement is terminated by a colon, introducing a new block, so we indent 4 spaces and create an empty list which ultimately will hold all of the words from the text. Next, we open a for loop which will work through the story. Recall that for loops request items one by one from the term on the right of the in keyword, in this case story, and assign them in turn to the name on the left, in this case line. It so happens that the type of HTTP response represented by story yields successive lines of text when iterated over in this way, so the for loop retrieves one line of text at a time from Dickens's classic. Note also that the for statement is terminated by a colon, because it introduces the body of the for loop, which is the new block and hence a further level of indentation. For each line of text, we use the split method to divide it into words on white space boundaries, resulting in a list of words we call line words. Now we use a second for loop nested inside the first to iterate over this list of words, appending each in turn to the accumulating story words list. Finally, we enter a blank line at the 3 dots prompt to close all open blocks. In this case, the inner for loop, the outer for loop, and the with block will all be terminated. The block will be executed, and after a short delay, Python now returns us to the regular triple arrow prompt. At this point, if Python gives you an error, such as a syntax error or indentation error, you should go back, review what you have entered, and carefully re-enter the code until Python accepts the whole block without complaint. If you get an HTTP error, then you were unable to fetch the resource over the internet and you should try again later, although it's worth checking that you have typed the URL correctly. We can now look at those words simply by asking Python to evaluate the value of story words. Here we can see the list of words. Notice that each of the single quoted words is prefixed by a lowercase b, meaning that we have a list of bytes objects where we would have preferred a list of strings. This is because the HTTP request transferred raw bytes to us over the network. To get a list of strings, we should decode the byte stream in each line into UTF-8 Unicode strings. We can do this by inserting a call to the decode method of the bytes object and then operating on the resulting Unicode string. The Python REPL supports a simple command line history, and by careful use of the up and down arrows, we can re-enter our snippet. When we get to the line which needs to be changed, we can edit it using the left and right arrow keys to insert the requisite call to decode. Then, when we rerun the block and take a fresh look at story words, we should see we have a list of strings. We've just about reached the limit of what's possible to comfortably edit at the Python REPL, so in the next course module, we'll look at how to move this code into a Python module where it can be more easily worked with in a text editor.